Hello everyone. So today let's discuss the this one Edmond's Karp algorithm, right? So previously we had discussed on the topic Hopcraft Karp algorithm. So let's get into the definition part here. So let just give me a second here. So let's get into the definition part here. Let's see what the definition part say here. The Edmonds Karp algorithm is an implementation of the Ford-Fulkerson method, right? So it is the implementation of the Ford-Fulkerson method just to calculate the maximum flow into the flow network, maximum flow in a flow network, right? So this one just keep this on mind. What does it use? Basically, it uses BFS, right? Breadth first search, just to find the shortest augmenting path in terms of the number of edges. So just remember one thing, whenever it comes to graph, so if you are writing algorithm, if you are solving the problem, so if you want to go with either the BFS or the DFS, choose the BFS. It will solve most of the problems. So it will solve most of the headaches actually, right? So opt for the BFS rather than the DFS, right? So this is fine, I believe. It uses breadth first search BFS just to find the shortest augmenting path in terms of the number of edges. This is fine. Let's get into the explanation part. In a flow network, suppose if you are considering a flow network, the goal is to push as much flow as possible from a source node S to the sink node T. Right? There will be two nodes. One is source node S actually. This one. There will be two nodes. One is source node as well as the sink node. Source node will be considering as S and will be considering sink node as T. So what is our main goal here? The goal is to push as much as possible. This one in a flow network. Goal is to push as much this one flow as possible from the source to sink actually, right? So two nodes SNT. So Ford Fulkerson method by repeatedly finding. So see here, Ford Fulkerson method works by repeatedly finding the argument paths and increasing the flow along them. Increasing the flow along them. It goes with repeatedly finding augmenting paths and increasing the flow along time, right? So now, flow along them, sorry, not time. So now, what does the Edmonds Cup specifically it does? It uses BFS, breadth first search, to always find the shortest path, right? Only it considers only the fewest edges, right? So it will be making use of BFS to always find the shortest path, nothing but it will be making use of the fewest edges from S to T. So the BFS approach, this one approach ensures the algorithm runs in big of V into E square time, right? So where V is nothing but the number of vertices and E is nothing but the number of edges. We know this, right? So let's move on with the step by step. What are the steps that will be going with basically? Let's discuss that. So first, what we will be doing, we will be initializing the flow in all the edges to zero. We'll be initializing flow in all the edges to zero, right? Initially. Next, while there exists a path from source to sink in the residual graph that found via DFS, so BFS, sorry, then we will find the minimum capacity. We'll find the minimum. What we'll first do, we'll find the minimum capacity. We'll perform the BFS, and while there exists a path from the source to sink, right? Uh, that this one in the residual graph or in the graph basically, we will find the minimum capacity along the path. Also, we'll apart from finding the minimum capacity, will augment the flow along the path by this minimum capacity as well. Let's see that one in the action. For this one, I have already written the algo. So let me explain you step by step what we are doing here, right? So one second. Yeah. So first what we have done here, from collection import DQ. So what we are doing here, we are just importing the DQ for the efficient BFS queue operations. We'll be making use of the queue. So we have imported the DQ from the collections. This is fine. Next, we are going with a BFS function here. BFS function, right? So we are going with CF source and sink as parameters here. So this function, BFS function, this we are making use of just to find the augmenting path in the residual graph as discussed in the explanation, right? So parent equals minus 1 into n, whatever I have written here. So what it does, it keeps track of each node's parent in the BFS path. It keeps track of each node's parent in the BFS path, right? So q dot append whatever I have written here, this one line number 33. So this one append of source, we are starting the BFS from the source node. We are starting the we are performing the BFS or we are starting the BFS from the source node, right? So this is fine. Now let's move on with the for loop here. For v in range of n we have considered here, right? So we are checking all the possible neighbors of the node u. We are checking all the possible neighbors of the node u. So let's come to the exam, this one line 37. So this is very important. Basically, what we are doing, if C of uv equals f of uv greater than 0 and parent of v equals minus 1, what we have, whatever I have written here, this is the residual capacity, right? So if the residual capacity exists and suppose if the node is not visited, right? In that case, what we will do in that case, so we will mark the parent for the path reconstruction. We'll mark the parent for the path reconstruction. Suppose if the residual capacity exists and the node is not visited, then only we'll mark the parent for the path reconstruction, right? So then what about this if condition? This one. If sync node, the other node we are considering, source and the sync we are considering, right? The other node, if the sync node is reached, then we have to, or then we will, this one, return the path basically. Then we will return the path, this part. Then we'll return the path. Right, so this is fine, I believe. This is fine, I believe. Next, let's get into the this one. What do we call? Edmond's Karp, this one, main function or the main method here. This is fine. So now, yeah, f equals 0, this one, whatever I have written here, line number 46. So this one, we are initializing all the flows to 0 initially, right? We are initializing all the flows to 0. This is fine. Max flow of 0, this is fine, we know this. So let's move on with a while of true. Max flow, we are initializing this one with a currently with a digit 0. This is fine. So while of true, so this one, we have to repeat until no more augmenting paths exist. So we are just going with a while loop here. This is fine. So path flow, whatever I have considered here, the line number 56, this one, path flow equals float of infinity. So we are initializing the path flow to the infinite or to the infinity just to find the minimum capacity, just to find the minimum capacity, right? So this is fine, I believe. Yeah. Now next, this one, path flow equals mun of whatever I have written here, line number 59. So this one, we are finding the bottleneck, this one, capacity along the path. So we are going with the min of path flow, C of uv minus this one, min of path flow. This is fine. Path flow. This is fine. This one, we will get the minimum from C of uv minus f of uv. So what is this basically? We are finding the bottleneck capacity along each path, right? So f of uv, whatever I have written here, this one, right? So f of uv, this one equals path flow, and f of uv equals f of uv plus path flow, and f of vu equals f of vu minus path flow, whatever I have written here, f of vu minus path flow, this one. So this one, line number 66, f of uv equals f of uv plus path flow. Basically, we are updating the flows in this one. What do we call? We are updating the flows in both the directions. This one, these two lines, 66 and 67. We are updating the flows in both the directions. We have to update the flows in both directions, right? So this is fine. Finally, let's come to the this part. Maximum flow plus path flow. This one. Maximum flow equals max flow plus path flow. Line number 70. So we are adding the current path flow to the total maximum flow. Yeah. Finally, we are returning the calculated maximum flow here. This one, line number 72. So this is it for the all go. Right. So we are just returning the computed this one, maximum flow. Right. So here when I write, so we are considering the example usage here, right? So this is the capacity matrix that we have considered. Source is 0 and the source node we are considering from the 0, and this one, what do we call, sync node, we are considering 5 actually, 0 1 2 3 4 5. Yeah. Sync node we are considering 5. Source 0, sync node we are considering 5. This is fine. Now what is the output that we need to get here? So for this particular this one, whatever we have considered the example, the output that we need to get here is 5. So sorry, 23. From the this one. Recently I was solving some problem. Sorry. This one, we have to get the output 23. Why we need to get the output 23? You can just go through the input, whatever I have given. So you have time, if you have time. So now, first, let me tell you one thing. So we are just printing this. We are going with a print for the interactive purpose right here. We are calling Edmond scope along with a C source as well as the sync. So the output that we need to get here is 23. Why? Let me explain. Just listen to this carefully. So basically, algorithm Uh, accordingly with what we are discussing here, source 0 and sink 5, the algo found the maximum flow from source 0 to sink 5 here in this case, right? So we are, that is the reason we are considering here source 0 and sink 5, right? The flow of 23 here, the flow of 23 is the sum of flows through all the augmenting paths that could reach the sink. You can just see what is this 23 basically. The flow of 23 is the sum of flows through all the augmenting paths that could reach the sink. And one more thing here, each augmenting path that this one added some flow without exceeding the edge capacities, and also whatever the BFS code that we have written, right? So BFS ensures the shortest paths were used first. That is the reason we are making use of the BFS. So that is how, that is the reason we got 23 here, right? So each augmenting path added some flow without exceeding the edge capacities, and BFS ensured the shortest paths were used first, right? Again, the flow 23 here is the sum of flows through all the augmenting paths that could reach the sink, right? So we are making use of the source 0 to sink 5, right? So this is fine. Yeah, this is it for the algorithm. So this is it for the algorithm, right? Edmond's Karp algorithm. So now we are done with the Edmond's Karp algorithm, right? So let me summarize whatever we have learned so far. So just try to remember these 2 to 3 points or 3 to 4 points. So this one, Edmond's Karp algorithm is BFS based Ford Fulkerson for the maximum flow. Right. So usually we make use of the Ford Fulkerson, this one Fulkerson method to find the maximum flow. So in this case, it is nothing but the Edmond's Karp algorithm is nothing but the same. This has been a bit extended. We'll just make use of the BFS, right? BFS, this one to find the shortest path based on this Edmonds Karp is BFS based Ford Fulkerson for the maximum flow. Extension of the Ford Fulkerson method. Basically Edmonds Karp algorithm, right? So now what it does, it guarantees the polynomial runtime. Polynomial runtime in the sense overall time complexity for this algorithm would lead to pico of V into E square. Pico of V into E square. Fine. Now the third point, the third main point here is we will iteratively find augmenting paths. So one is we will be going with a iteration here, right? We will be iteratively finding the augmenting paths, updated flow along the path, and it repeats until no path exists, right? So this is one of the important points. This is fine. And the final one, the fourth one is the result is the maximum flow. The result is the maximum flow from source to sink. From source to sink. Not here in this case. Source we have considered 0, sink we have considered 5. Example, we have considered this one capacity matrix. Output that we got here is 23. Right, that we need to get here is 23. So I didn't run the code at all, I believe, right? So let me run this one. We have to get the output 23 actually. Let's see. I have explained you the thing, right? So this is fine. I'll just give Control J here. Python file name dot py. Yeah, maximum flow we are getting 23, right? So this is it for the algo mainly. This is it for the algorithm, right? So next, what we'll be doing, we'll be discussing on the Dinix algorithm, right? So we'll be discussing on the Dinix algorithm. For now, this is it. Thanks for watching, guys.